Okay, so today's a little bit different in that it's the first quiz you're going to have for the semester. It shouldn't be that bad, hopefully. Obviously, it's easier for me to say as a professor than it is for you to say as a student, but I try not to be too tricky with the quizzes. Usually it's like an easier example of something we did earlier in the week, so it shouldn't be too bad. So there's 10 minutes I wanted to dedicate to today's lecture where I'm just going to be finishing what I want to cover in section 1.3. And then the next 20 minutes after that are going to be a practice quiz. And then the last 20 minutes of class are just going to be the quiz itself. So you'll have some exposure of what the quiz is going to look like before you actually take the quiz. We have the time to do it this week. I don't know if we're going to have the time to do it every week, but we're on schedule, so we may as well. Plus, it's the first quiz of the semester. So I want to make it so it isn't as stressful as it could be otherwise. And so where we left off on Wednesday's class was we were looking at propositional equivalences. So this is something you'll have to do on today's quiz where you'll create some sort of truth table and you want to make sure that two propositions are equivalent to one another. So we've had some practice with this on Wednesday when we did this kind of proof, right? We wanted to show that this statement or proposition truth value and this proposition ended up being equivalent to one another. So these had the same truth values. Or you can look at the biconditional and see that it's a tautology either way. So there's two more examples I wanted to go through. And these are the examples on page 8. So there's two examples on page 8 I want to go through. I would say I've already posted the solutions online. But I will say like the examples on page 9 and 10, I kind of just added these in case we needed more things to do throughout the week. So you don't have to know about satisfiability or like the dual operator. Okay, I'm not going to cover it in class. You don't have to know about it. So I'd say like past page 8 of the section 1.3 notes, you don't have to know anything. That's what I'm saying. Okay. So for this first example, what it wants you to do is it wants you to show that these two propositions are logically equivalent to one another by developing a series of logical equivalences. So this is similar to the last problem that we did on Wednesday. So you want to make use of this table and all the identities they have in this table in order to go from this statement to this statement via a series of equivalences. So I'm just going to go from this to this. Maybe you can go backwards, but I feel like this is easier. Like it's easier to go here to here than it is to go from here to here. And so let's just write down the original statement first. So we have not P or not P and Q. And so I would recommend going from the outermost term, right? We have like everything is inside of a parentheses here, and we're applying a not to this parentheses. So you should probably determine like how do we like handle this not. In the interest of time, I'm just going to kind of say it, even though I like usually asking people for help. Here you want to use De Morgan's laws, right? We talked about De Morgan's laws a little bit in class on Wednesday, right? So if you apply a not to an or, it becomes an and you apply the not to both sides. And then if you apply a not to an and, it becomes an or, right? So the not or the negation flips ands to ors, and it flips ors to ands. That's something that's worth remembering in this class. It's going to show up pretty frequently. And so really we're applying a not to an or right here. So really we're doing like not P, this not or is going to become an and then we apply the and to this or the not to this entire thing right here. So by De Morgan's laws, this is equivalent to not P and not, and then in parentheses, not P and Q. So again, this is De Morgan's laws. I'm just going to write De Morgan over the equivalence. And then we can do the same thing over again, right? There isn't much we can do with this not P at the moment, but we do have like a not, and then we have not P and Q. So you can again distribute this not to this parentheses right here using De Morgan's laws again. So you don't have to do anything with the first not P. We're not going to change anything, as well as the and. Instead, we're going to distribute this not throughout this parentheses via De Morgan's laws. So this is the same thing as kind of like not. Ooh, how many parentheses do I really want here? So this is the same as like not P or not Q. Sorry, that not very good. And so we know as well that if you do not P, the knots cancel out with one another, so it just becomes P. So this is equivalent to not P and P or not Q. Any questions so far? Again, this was the De Morgan's law. I should be labeling these. This is De Morgan. Okay, and so we're still have some ways to go until we reach this point right here. The next thing we can do, this is something we proved in class as well, is you can distribute a term through an and via like the parentheses. Like there's a distributive law for ands over parentheses. Let me see if I can find where it shows up exactly. Yeah, we have this law right here, right? So if you do P and Q or R, it's the same thing as P and Q or P and R. You can think of and as like multiplication and or as addition, in which case it's just the distributive law that you're familiar with from algebra, right? If you do like P multiplied Q plus R, it's the same as P times Q plus P times R. That's one way of remembering things. So we can apply that here. So this is the same thing as not P and P or not P and Q or not Q. And then we know, I'm going to go a little bit faster because I said we're going to spend 10 minutes and we haven't even started the next problem yet. Not P and P, we know is a contradiction, right? You can't have not P and P, so that's always going to be a false. That's going to be false. So we have false or we have not P and not Q. And then this is going to be entirely determined what the truth value of not P and not Q is going to be, right? If this is going to be false, then we're going to output false when we OR it with false. If this is true and we OR it with false, then it's going to be true. So this, like the false here doesn't really do anything, right? It's entirely dependent on what the truth value of this is going to be. So this is the same thing as not P and not Q, which is what we wanted to show, right? We started with this proposition and we ended with this proposition. And then between the two, we have a bunch of equivalences. So the statements are logically equivalent. Again, you don't have to do it like this on the quiz. I'd recommend just doing a truth table, but we're learning right now, okay? We're just learning. Any questions about this example? Okay, maybe I'll go a little bit quickly through the next one, just because I want to make sure you have time to work on the practice quiz and then the quiz itself. Okay, so before getting started with this one, for this one, we have P and Q implies P or Q is a tautology. We've already seen the following. So this is what we did at the top of page 6, I believe, the first example of page 6. We've shown before that P implies Q is logically equivalent to not P or Q. In general, it's a good idea to convert things into nots, ands, or ors to make life a little bit easier for you. So we're going to start with P implies Q implies P, or P and Q implies P or Q. From what we have above, this P and Q serves as our P, and this P or Q serves as our Q because this is the left hand, like on the left side of the arrow. This is on the right side of the arrow. And so we can say that this is going to be equivalent to not P and Q. And then this is going to be or just P or Q. Right? I'm just making use of this fact right here that we proved in class, I think on Monday or Wednesday. And then, I mean, you kind of noticed already, we use De Morgan's laws a lot, right? So that's kind of the most important rule, I would say. So we can distribute the not throughout the parentheses here. This is the same thing as not P or not Q. Again, the not flips the and, so that way it becomes or, and then you distribute the not to both terms of the proposition, or the and, I guess. And then this will be P or Q. And so what we can note here is all the operations we have are ORs at this point. And so let's just look at what we can do with this, right? If you look up at the table above, there's, I guess, two major rules we can make use of when we only have ORs around. For instance, we have the associative laws, which says that if you're doing a bunch of ORs together, the way you do the parentheses doesn't matter, right? Like this is saying, like if you have 3 ORs or 2 ORs, the parentheses don't matter. So we can get rid of parentheses for this problem. And then if you look at the commutative laws, it says that it doesn't matter the order in which the term or the propositions show up with the or. So if you do P or Q, it's the same thing as Q or P, so you can switch the order around. So if you combine those two observations, the first associative law tells you that this is the same thing as, like, you don't need parentheses at all. This is not P or not Q or P or Q. So this is by associativity. And on the solutions, I have more detail. I just want to make sure I finish this so it's time to work on the practice quiz. And then by commutativity, we can switch the order of these terms in whatever way we want to. Does anyone see how we should be switching terms around to make it so it's easy to work with?
About switching them into the groupings of if we put them in parentheses, first grouping in parentheses would be not P or P. So if the second pairing be not Q or Q, as that would naturally make it always true.
Yeah, exactly. So you want to switch the order so that way we have not P or P and then not Q or Q. This is the first thing we did in this section. Not to give you motion sickness, but I want to scroll up. We saw before that if you have any proposition and you OR it with its negation, you always get a tautology. So that's exactly what we have here, right? So P or not P, that's always going to be true. And then not Q or Q, that's also always going to be true, right? So this is what we did in class on Monday or Wednesday. And so if you have true or true, it's always going to be true, right? So we have a tautology here, which is what we wanted to show. So in the solutions that I've posted on Canvas, I actually label the equivalences so you can more easily see like what steps I'm taking where, but I didn't want to spend too much time on this one. There's other things to think about today. Any questions about this example?
Pencil sharpener might be.
I don't know. Yeah, and then again, as I said, these next 2 pages you don't have to worry about. If you want additional practice, it could be good to go through, but it won't show up on the exams. Like the satisfiability and the dual operator, you don't need to know. Okay, let me stop recording for a second, then I'll pass out the practice quiz. Okay, so I've already said this